Chris, when's the other projects gonna be put up on campus?
My goal is to get it out to you today. So we're finally far enough, we're finally getting far enough in the curriculum for this second project idea. And it's a little bit on the late side for it. So I apologize for getting it to you so late, but even if I got it to you before now, I don't think you really would have been able to do too much design or get started. Because the last couple of class periods, we've introduced the material for it and we'll finish it up today. So it is what it is. I can try to get it out earlier or go over this content earlier. Now I know how that material lays out and where this appears at the pace we've been going already. So, all right, where were we? We had talked about the context-free grammar to NPDA that modeled the, oh, what the heck? This is the wrong slide deck. This is the wrong slide deck. Wrong one here, interesting.
It's a lot of technical problems, but I was there for a couple of events. Yeah. The first was all that was paid.
Just a second.
Then I do two in there. That's so much awesome. It's close. That's why.
All right, we were talking about context-free grammars being transitioned into NPDAs and what that process was like to model the LL parse process. So we said we're going to end up with three states: a starting state Q0, a parsing state Q1, and a final state Q2. As we transition from Q0 to Q1, we push S onto the stack. We need some productions within Q1. We need to handle the ability to replace the left-hand side with the right-hand side. So at any particular point, if the top stack symbol is a non-terminal, we can non-deterministically decide which production that has that as its left-hand side to apply. So if we have multiple options, something like A arrow something, A arrow something else, and A is the character, capital A, that's on top of the stack, then we pop and non-deterministically choose which one of those productions to apply. And as we've talked about before, you can think about this as having extra threads. So you're just going to fork the program at that point and try them both. And maybe each of those threads will fork eventually, and you'll be trying a bunch of different possibilities. But the idea is if any of those threads return, yes, I can generate this string, then we accept it. So we need all of those productions in the non-deterministic pushdown automata so that we can make those forks and determine if any one of those threads is going to return true. We also need an additional parsing edge, I guess, for we need the ability to, if the character that's on top of the stack is a terminal, we need the ability to read that in the string. To be able to say, can we consume this character and move forward? What happens if we can't? What happens if we see that the top element of the stack does not match the next character in the string? What do we do?
Would it just not be a language zone?
Yeah, we just reject right then and there. And since we have so many ongoing threads, that just kills that thread, and all other threads are still going because only one of them needs to return true. So we gave an example of this. So we got this far, right? I think we did. We did this, and then we saw the image that people memed. So here was the grammar. We start at Q0, we push S onto the stack and transition to Q1. So that would be the transition for that. We need a transition rule for each production. So this says that we're going to replace the left-hand side with the right-hand side. When we pop the left-hand side from the stack, we'll replace it with one of the right-hand sides. Non-deterministically, both of the right-hand sides. So here are the transition rules for that. Note that these are actually 4 transition rules, not just 2. And they represent the fact that we're going to be popping an S or an A here, and there are 2 possible productions that we could apply for each one of those that refer to the S productions and the A productions. We then need transition rules to what we're going to call shift the input symbol on the stack. So whenever we read an A, we can make a lambda transition basically, or sorry, we pop the A off the stack and move on to the next character in the input string. So if we see an A, then we're going to pop it and move on. Read the A in the string. Then we need the final state transition that is going to determine acceptance. We can only do that if we see the bottom of stack symbol Z. So we do all of the parsing in Q1, and if we reach a state where both the stack is empty and we are at the end of the input, then we accept. So this sounds just like a non-deterministic pushdown automata that we've seen before. And this will work, and it models the LL1 parsing process. But we're going to be reading from left to right and replacing non-terminals. What issue do we see with this process, or what concern do we have with this process at this point? If the purpose of an LL grammar is to actually take a program written in a high-level language and convert it down into bytecode or assembly or machine code, then we need some way of actually doing that process. Can we model that process with an NPDA? We can model it, but do we have an infinite number of threads to run on? No. We need some way of turning this non-deterministic process into a deterministic process, and preferably one that is going to be efficient, rather than just there are an exponential number of threads going right now. We need to be able to look at all of them in parallel. So this isn't a complete solution, but it's the start of one. So here's the resulting NPDA. We just end up with a bunch of transitions in Q1. We push the start non-terminal onto the stack to go from Q0 to Q1. We go through some non-deterministic work in Q1, and eventually, hopefully, there is some thread that is at the end of the input, sees the bottom of the stack symbol, and is able to transition to an accepting state. Let's look at how we can actually go through and model this parse given an example string. You'll end up with a diagram that looks kind of like this. So the NPDA that we just saw, a look ahead of size 1, so we're only able to look ahead one symbol. Now remember that look ahead is designed to be able to break this non-deterministic tie, to be able to say something like, if the next character in the string is an A, I need a production that is capable of the next symbol that it produces, the next terminal that it produces is an A. If there are 2 possibilities and one of them produces an A first and one of them produces a B first, then we know we have to pick that first production. So the look ahead can tell us what to do when there is ambiguity. If we have an LL1 grammar, then a look ahead of 1 is all we need to be able to make that decision. So we're going to do this over the string ABCAB. The stack starts out empty. We are in state Q0, and the next symbol in the string is the very first A. So this look ahead of A in step 1 refers to this A in the string as the next character that needs to be read. So we transition from state Q0 to state Q1. As we do this, we push S onto the stack. Our look ahead is still A because we haven't actually consumed any terminals. What happens next? What happened when we went from step 2 to step 3?
The S was consumed and pushed the ASB.
Yeah, we did one of these transition rules where we said we can not read anything from the string, pop an S and push an A capital SB. So we followed that transition rule in Q1, and that made the associated transition between, we went from state Q1 to state Q1 without consuming any symbols. We popped the S and pushed an A capital SB. So that's just one of the transitions defined in the NPDA. How did we get from step 3 to step 4? We read an A from the string. So we mapped this A to that A. So this got popped. The look ahead changed from an A to a B. It says the next character that we need to be able to produce on top of the stack is a B, this B in the string. Great. So now we need some way of producing that B. What did we do next?
Essentially resolving the S because it'll be an A.
Yeah, we did one of these transitions. We're back in the grammar. We had S arrow A. We can see that in this rule right here, pop an S, push an A, make no change in the string. So we do exactly that. The look ahead stays the same. Go from Q1 to Q1, look ahead stays the same. We pop an S and push an A. Great. What do we do next? We have a grammar rule that A can be replaced with B capital A. So we're going to pop the A, push B capital A. This doesn't read anything in the string to do so, so we stay in the same state and we have the same look ahead character. But now we've generated that B that is the look ahead that we want to be able to do. So once we have that, we can do what's called a shift, and we can shift the string from reading the B, we can actually read the B and move the look ahead to C as we pop the B off the stack. Great, so now we need some way of producing a C, but there's a rule in the grammar that lets us do that directly. We can replace the capital A with a lowercase c. So we're going to do that. Now we've produced the C that is the look ahead. So we're going to consume the C, moving us up to this A. Hey, look, it happens to be perfectly on the stack for us. So now we can pop the A and read the B, pop the B, and now we're at the end of the string and we have the bottom of stack character. So we can move from state Q1 to state Q2. And this $sign at the end just tells us again that we're at the end of the string. So we can get all of this information from the first and follow functions that we talked about. So first and follow, we'll be able to generate which rules, when there are multiple different ways that we could resolve this. How do we know here to do this A to a B capital A and not to a C? And here to do the C rule and not the B capital A rule. Right there, when we have that ambiguity, when we have multiple ways that we can do it, in an NPDA, we can just fork. But in a deterministic, fast algorithm, we need some intelligent way to produce that. And that's what that look ahead allows us to do. The look ahead tells us what happens when we take first of A. What is the set of things that we can get from first of A? What are the follow rules of A? What can follow an A? Between those two pieces of information, we can decide if this is an LL1 grammar, which production rule to apply. So as we do this, we construct what's called an LL1 parse table. This is the table that's going to tell us whether or not this process was good enough. So if you take the NPDA as input and the associated look-ahead character, you can store all of that in a parse table. The rows of the parse table are going to be the non-terminals that are in the grammar. The columns are going to be all terminals in the grammar, as well as the addition of the end of string marker, this $sign. So how do we actually fill out the table? We're going to refer to each cell of this table by LL of row column. So it's just like an index into a 2D array, where the 2D array is called LL. So for every production in the grammar, we need to find at least one associated place for it in the table. The way you're going to do it is you're going to look at each terminal in first of the right-hand side of that production. For that terminal, you're going to add the right-hand side of this to LL of the row that is the left-hand side of this production. And then that terminal that is in the first of the right-hand side of that production. This will make much more sense with an example. However, just like with follow, if lambda appears in first, then you have to add all of the elements of follow. At the end of this entire process, we get the table. And I seem to have forgotten to correctly animate the images on this next slide, so hang with me. So the example for this would be to build the parse table for the grammar that we just used. We first need to calculate first and follow for all non-terminals. We have a bit of experience doing this now, so here is the result of first and follow for both S and A. As we construct the table, we need to look through each production. So S arrow ASB. We see that it goes in row S, column first of ASB. We know that the first of a terminal is itself. So it tells us when we see that we can get from this non-terminal to start a string with this terminal by applying the production this arrow this. If that makes sense. There is in the grammar S arrow ASB, and it's the production to apply if what's currently on the stack is S, and the next thing you want to do is consume an A in the string. It tells you that that is the production to use to do that. S arrow capital A, we now need to know what is first of capital A. Well, first of capital A is the set B, C, because they're the terminals that can be first consumed after seeing the non-terminal A. So we add S arrow A into the generation from S to lowercase b and capital S to lowercase c. Does this process make sense? People see what's going on and what the use of this table is, how it's generated. We're just going production by production and adding right-hand sides to this table in the appropriate place. We can see that for A, this is the production that we want to use if the next character in the string is a lowercase b and we want to produce that. So we put that production in the going from A, capital A to lowercase b, that's the production to use. And the same thing, we want to generate a C from A, we put the right-hand side in the table. What do we notice about this parse table? Would it be possible for there to be multiple elements in a cell? Are we guaranteed to only have one thing in a cell, or could we have two different right-hand sides in a single LLXY?
feel like you could have multiple, but I'm not sure.
Yes, you can. You can absolutely have multiple. What does that tell us? If there were multiple in a cell, how would you evaluate that?
Both, or would you have to look at like the next one after it?
Yeah, the idea is then there's ambiguity with look ahead of size 1. So maybe you have to try a look ahead of size 2 or a look ahead of size 3. So the look ahead will scale based off of the ambiguity of the grammar. Like, let's say there was a production here, S arrow lowercase a, and that was it. Then in this cell, we would have two elements. From the non-terminal S to the terminal A, we can apply multiple different productions. Which production would we have to use for that? Who knows? With a look ahead of 1, knowing that we just need to generate a lowercase a, that's going to be really difficult to do. We don't have enough information to make that decision. But what would happen if there was a look ahead of size 2 and we did that? If you looked ahead twice in the string and saw A here, you would know that you could not apply S arrow A because that would terminate the string. You would need to apply S arrow ASB right now. If you saw a $sign saying that we've reached the end of the string, then we would know not to apply this rule because this can't generate A followed by the end of the string, but this can, this new symbol that we just added. So that look ahead would tell us which production to apply.
The 1 in LL1, same as the look ahead of 1 then?
Yeah. LL1 just means that there is a look ahead of 1. And the LLK means that there is some constant look ahead. If you look ahead some number of symbols in the future, you can make an unambiguous, you can turn this non-deterministic PDA into a deterministic algorithm to determine which production to apply. So here's the whole algorithm in all of its beauty. It's going to use push, which is just a stack push, pushing the string W onto the stack. You begin with the rightmost character and end with the leftmost character, such that the leftmost character ends up on the top of the stack. Top returns a copy of the top symbol of the stack without removing it. This probably sounds like things that you have implemented in data structures, hopefully. Pop removes and returns the first symbol of the stack, and get returns the next look ahead symbol in the input string. So these are all of the functions that the algorithm will use. How do we know when we're done? We can either accept, which the algorithm will show you when to accept, then the string is in the language. If we reach an error state, then the string is not in the language. So this all just uses the functionality of any built-in languages stack. And if this isn't implemented for some reason in the language of your choice, it's not too bad to implement for yourself. So here it is. We will push the start non-terminal. We'll set the look ahead to the next character in the string. While the stack is not empty, we will figure out what's on top of the stack. If the symbol is a terminal, then we need to check if that terminal is the same as the look ahead. If it is, we can pop that terminal from the stack and move ahead in the look ahead, which is exactly what we showed in the visual example of actually going through the NPDA with a stack. Otherwise, it's an error. If the symbol is a non-terminal, which here they call a variable, then we will look up the LL symbol look ahead. If that cell is empty, then we declare that to be an error. But if that cell has at least one element in it, then we will continue. And we will pop and push the right-hand side that is found at LL symbol look ahead. If that's not possible, then we error. If the look ahead is not the end of the string, then we have to error at the end of that loop. Otherwise, once we go through this entire process, we accept. I supply this because this is going to be an important part of the project. So you'll be implementing first and follow and the LL1 parse table for a grammar and a file. So I tried to incorporate pseudocode everywhere that you would need to implement. So first has pseudocode, follow has pseudocode, and now LL1 has pseudocode. So as part of this, you would be calculating first and follow. But it would allow you to build the LL1 parse table to determine, yes, we can figure this out with a look ahead of 1, or no, we cannot. Shall we go through an example? All right, same grammar as before. Here it is one more time. Go ahead and actually apply LL1 to the string ABCAB. So go ahead and show the contents of the stack at each step, show the contents of the look ahead at each step. So write all of this down, and I will go back to the LL1 table so that you can make sure you're looking at the associated table. So this is the exact same problem as before. So this should look very familiar, except that instead of having the states and tracing it through the NPDA and the NPDA's transitions, we're going to use the LL1 parse table instead. So we're not storing the state that we're in an NPDA. We're instead using the LL1 lookup table. So does everyone have this written down? All right, so you can think of going through this algorithm. And you want to follow the process of producing, so here's the table. So same grammar, we already produced the table, but go ahead and walk through the generation of what you want and see if there's any ambiguity at any point in your derivation. Does this make sense? Does everyone know how to get started? any other information we need. This is the stack contents and the look ahead. We also have our table for reference. First step of the algorithm says what? Push capital S onto the stack. So we're gonna have a stack, Z, capital S, look ahead is still an A. All right, now we want to derive, we're at an S, we want to derive an A. So this tells us which production to apply here. We have some ambiguity, we could either do A capital S B or capital A. But since we want to derive this look ahead A character, we're going to use this rule. So we're going to pop the S and push A capital S B. So look ahead is still an A on the stack with Z, and we want A capital S B from right to left. And note that now we've produced the A that we want to use to read. Great. So now we can pop the A and move ahead in the string. I guess we want something like A, B, C, A, B. So we're moving from A to B as the look ahead now. We popped the A, so we have the bottom of stack character, a B, and a capital S. So now we want to produce the B, the look ahead from this S. So we're going to look up in the table, we want to go from S to B, so we want to apply that rule. So we'll replace the S with an A. Now we're down in the A row, so we want to go from capital A to lowercase b. And here is the rule to do that. So we're going to replace the A with B, A. So A, capital A, lowercase b, and now we find the lowercase b that we want. Note that we don't need the NPDA. We don't need the list of transitions in the NPDA anymore. And we also have a deterministic algorithm. There's no ambiguity at any point because of this table. So we can now shift the look ahead and pop the B. So Z, B, A, capital A, move the look ahead from B to C. Now we want to go from capital A to C, which we can do directly. So we will do exactly that. Look ahead is still a C, Z, B, A, C. And now everything that's left for us is already on the stack, so we just have to do shifts. We pop the C. C, B, A, look ahead is now the A. That happens to be exactly what's on the stack. So we can pop it. We will move this over to B. A there, nice. And now the look ahead is the end of string, and we have the bottom of stack character. When we reach this state where this combo is what we see, the bottom of stack character and the end of string marker, we know we can accept. So this is what tells us that this string is in, it can be generated by this grammar. Questions on this process? How using this table turned this into a deterministic process from our non-deterministic state machine? So you can kind of sort of throw away the NPDA in this. This is the process we care about here, but you can think of the process we went through to generate the NPDA as one of the ways to reconstruct this algorithm if you ever lose sight of it. Intuitively, what is this process doing? We're just modeling the construction of an NPDA, except that this look ahead turns it into a deterministic algorithm, which we can now go implement in a single thread programming language on a single thread. All right, that does it for the day.